Hello viewers, welcome to my channel. This is Dr. Veka Venkateswarlu, Assistant Professor of Physics, Government Degree College, Autonomous, Hyderabad. Now I am going to start the syllabus of fourth semester. The paper name is Waves and Optics. In this, the first chapter is Waves. In the first chapter, we will discuss the fundamentals of waves and the transverse waves in the strings. Then we extend our discussion to the longitudinal vibrations in the bars and the transverse vibrations in the bars. So this is the first unit syllabus. The second unit is we talk about the interference. The third unit syllabus is diffraction, the types of diffraction such as Fraunhofer diffraction and Fresnel diffraction and applications. The fourth unit is polarization. So in the waves and optics consist of the four units. The first unit is waves, second unit is interference, third unit diffraction, fourth unit polarization. First, let us have a syllabus with the first unit. Yes. Okay. So already we know that um, the types of waves. So what are the types of waves? There are the two types of waves. One is the transverse wave. The second one is longitudinal wave. What is meant by the transverse wave? The wave in which the particles vibrate perpendicular to the direction of wave propagation, then that wave is said to be transverse wave. The wave in which the particles vibrate parallel to the direction of wave motion. Suppose the wave is propagating along x-axis, the particles of the medium vibrate parallel to the direction of wave propagation. Then that wave is called longitudinal wave. Example for longitudinal wave is sound waves and also the vibrations in the bars. Of course, the transverse vibrations also we can produce in the bars. The major part of the vibrations can produce easily in the bars is longitudinal vibrations. Clear, sir? Example for the transverse vibrations. The waves produced on the water surface, liquid surface, and the vibrations in the strings like the musical instruments, and also coming to the electromagnetic wave, all the electromagnetic waves are the transverse waves. Okay, so with respect to the medium, we can classify the waves in the two types, mechanical wave and the transverse wave. The wave which requires a medium for the propagation is known as mechanical wave. For example, the waves produced on the water surface. When we drop the stone on the water surface, then we can observe the ripples. So they are the mechanical waves. There the medium is water, right? So when the sound waves, all the sound waves are the mechanical waves. Here the medium is air. So when one person is, when I'm speaking, you are able to listen my voice. So here this is the longitudinal wave. All the sound waves are the longitudinal waves. Longitudinal waves are all what kind of that? This is the mechanical waves, right? Electromagnetic wave doesn't require the medium. Example, light waves, all the electromagnetic radiation. Electromagnetic spectrum, we know that. What is that? There are visible light, next infrared rays, microwaves, radio waves, next ultraviolet, X-rays, gamma rays. So that is a electromagnetic spectrum. All of you know that electromagnetic spectrum, all kinds of electromagnetic radiations are the transverse waves. Okay, right. Now, the wave equation. What is the wave equation? Um, General wave equation. The wave propagating along x-axis. The wave propagating along x-axis. So this is the progressive wave propagating along x-axis. It is represented by y is equal to a sine of omega t minus kx, where a is the amplitude, omega angular frequency, omega is angular frequency, right? K propagation constant, that is equals to 2 pi by lambda. A is the amplitude. So this is the equation of progressive wave traveling along the positive x-axis. Right. Coming to the wave propagating along the negative x-axis. So like this. That can be represented as y is equal to a sine of omega t plus kx. Okay. Along the positive x-axis, there we have the minus sign. The wave propagating along the negative x-axis, we have the positive sign. So this can be expressed in another modes also, because omega is equal to, we know, 2 pi by time period. K is equal to 2 pi by lambda. Substituting that, y is equal to a sine of 2 pi by t, capital 2 pi by capital Tt minus 2 pi by lambda, 2 pi by capital Tt minus 2 pi by lambda x. So from that, taking common 2 pi, then we get small t by capital T minus x by lambda. The same equation for the wave traveling along the positive negative x-axis, there you will get the positive plus t by small t by capital T plus x by lambda, right? In this, if you take the 2 pi by lambda also taking common, then we can write a sine of 2 pi by lambda into then lambda by capital Tt minus x. But lambda by t is the velocity of the wave. Substituting that, y is equal to a sine of 2 pi by lambda into vt minus x. For the wave propagating along the negative x-axis, then y is equal to a sine of 2 pi by lambda into vt plus x. Okay, so here we have written three forms of the wave equations of the progressive wave traveling along the negative x-axis and positive x-axis. Again, I am repeating the first one, y is equal to a sine of omega t minus kx, or y is equal to a sine of 2 pi into small t by capital T minus x by lambda, or y is equal to a sine of 2 pi by lambda into vt minus x. Okay, right. So here a is the amplitude, omega angular frequency, k propagation constant, right? Here y is the displacement. If you differentiate that with respect time, dy by dt represents The velocity of the particle. Velocity of the particle. Y is the displacement of the particle. Right. But velocity of the wave V is equal to F lambda, that is equals to lambda by T, that is equals to omega by K. So frequency F is the frequency, lambda is the wavelength. The product of frequency and wavelength is the velocity of the wave, lambda, but frequency is equal to reciprocal of time period, so that we get lambda by T. And also, in terms of angular frequency and propagation constant, V equal omega by K. So that we can check. Omega 2 pi by capital T, right? By lambda K, 2 pi by lambda. 2 pi cancel, lambda by T. But lambda by T is what? Velocity of the wave. So three formulas. V is equal to F lambda, that equal to lambda by T, that equals to omega by K. Right. Right. So this is the displacement of the particle. Dy by dt represents velocity of the particle. V is equal to velocity of the wave. Now, the wave equation of a mechanical wave. The general wave equation is dou square y by dou t square is equals to V square into dou square y by dou x square. This is the wave equation, second order differential equation. Dou square y by dou t square equal to V square into dou square y by dou x square, where V represents velocity of the wave in the medium. Velocity of the wave in the medium. Clear? If you consider the mechanical wave, for example, the transverse wave in the string, transverse wave in the water, or longitudinal wave, that is sound wave. These are the mechanical waves. For the mechanical waves, there V represents the velocity of that mechanical wave in that particular medium. So this is the general equation of general wave equation. Dou square y by dou t square equal V square dou square y by dou x square. Okay. Now let us derive the wave equation. Let us derive the wave equation for the transverse wave in the stretched string. So from that we can derive the formula for velocity of the transverse wave in the string. Right. So let us consider a transverse wave is propagating through a stretched string of length L, which is subjected to the tension capital T. Consider a string of length L, linear density mu, and which is subjected to the tension capital T. So when the string is when the wave is propagating through the string, the transverse wave is propagating through the string. Now let us take a small segment of vibrating string, that is AB. So for wave, transverse wave string lo propagate అవుతున్నప్పుడు small segment AB ని మనం కన్సిడర్ చేస్తున్నాం. So AB is the segment of vibrating string. So here the wave is propagating along the positive x-axis. అయితే segment యొక్క first end A position x అనుకుందాం. Segment B, segment యొక్క second end B position x plus dx అనుకుందాం. At the point A, tension is along this direction. So by resolving into the two components, T cos theta, this is the horizontal component, the vertical component T sin theta. Similarly, at the end B, T is the tension acting in the string. So there it is making angle theta with the x-axis. Therefore, by resolving into the two components, T cos theta 2 is the horizontal component, C sin theta 2 vertical component. Right. But here theta 1, theta 2 are very small. very small. Then t cos theta 1 almost nearly equal to t cos theta 2. So therefore, since they are acting in opposite direction, they get cancelled each other. So now only the two components, the vertical components are acting on the segment A. At the end A, t sine theta 1 acting vertically downward. At the end B, t sine theta 2 acting vertically upward. Right? So since here the angles theta 1, theta 2 are very small, we can take sine theta 1 is equal to sine theta 1 equal to sine theta 2. Sine theta 1 equal to nearly equal to theta 1, that equal to tan theta 1. But tan theta 1 equal to, we know the slope dou y by dou x at the position x. Sine theta 2 nearly equal to theta 2, that can be taken as tan theta 2. Tan theta 2 is the slope at the position b, that is dou y by dou x at the position x plus dx. So now at the end A, t sine theta 1, that is sine theta 1 equal to dou y by dou x at x. At the end B, t sine theta 2 component acting vertically upwards, where sine theta 2 equal to dou y by dou x at x plus dx. Therefore, the net force acting on the segment AB, that is AB of length dx, F is equal to t sine theta 2 minus t sine theta 1. T sine theta to how much? T into dou y by dou x at x plus dx minus t sine theta 1 is capital T dou y by dou x at x. So here take is taking common dou y by dou x at x plus dx minus dou y by dou x at x, equation 2. But according to the Taylor series, dou y by dou x at x plus dx is equal dou y by dou x at x plus dou square y by dou x square dx plus dou cube by dou x cube dx square by 2 factorial plus and so on. This is the infinite series. So considering the first two terms, comparing to the first two terms, the higher order terms can be neglected by considering that Fy is equal to T dou y by dou x at x plus dou square y by dou x square dx minus minus dou y by dou x at x as is written. The first term, the last term gets cancelled. Then Fy is equal to capital T dou square y by dou x square dx, equation 3. But the resultant force according to the Newton's second law, we have F is equal to m. So Fy is equal to m into a acceleration dou square y by dou t square, where m is the mass of the string, of length dx. So where mu, if mu is the linear density is nothing but mass per unit length, then the mass per the segment of length dx would be mu into dx. M is equal to mu dx substituted, equation 4. By equating equation 3 and 4, t dou square y by dou x square dx equal mu dx dou square y by dou t square. Both side dx cancel. Dou square y by dou t square equal capital T by mu dou square y by dou x square, equation 5. So this equation represents the transverse wave equations of the stretched string. Comparing this differential equation with the general wave equation, dou square y by dou t square equal v square dou square y by dou x square. Then from equation 5 and 6, it is very clear that v square equal to capital T by mu, v equal to square root of t by mu. So in this, this is the equation which represents the velocity of the transverse wave in the stretched string. So when the transverse wave is propagating through the stretched string, having the tension capital T and linear density mu, then velocity of the transverse wave v is equal to square root of capital T by mu, where T is the tension in the string, mu is the linear density. Okay, so what we discussed in this is simply we have taken this figure. So there we consider a small segment of vibrating length dx AB. So there at the point A tension T, at the point B tension the string T, by resolving to the two components at the point A, components T cos theta 1, T sin theta 1, at the point B, components t cos theta 2, t sin theta 2. Since theta 1, theta 2 are very small, t cos theta 1 gets cancelled with t cos theta 2. So there are only the vertical components acting on the segment AB, that is t sin theta 1 acting vertically downwards, t sin theta 2 acting vertically upwards. The resultant force is equal to greater value minus smaller value. So there the t sin theta 2 is greater than the t sin theta 1. That's why I have written Fi is equal to t sin theta 2 minus t sin theta 1. But again, we are taking the consideration since theta 1, theta 2 are very small, sin theta equal to theta, that equal tan theta. According to that, sin theta 1 equal tan theta 1, that equal dou y by dou x at x. Sin theta 2 equal theta 2, that equal tan theta 2, that equal dou y by dou x at x plus dx. And applying the Taylor series. So we have written equation 4, equation 3 and 4, equating 3 and 4. Finally, we got dou square y by dou d square equal capital T by mu, dou square y by dou x square. So this is the equation we are comparing with the general wave equation, right? Then v square is equal to t by mu, v equal to square root of t by mu. Okay.